All right, in this video, we are going to work through an example of node analysis. This is a process very similar to what we saw in the previous video, mesh analysis, except instead of analyzing the circuit using mesh currents, we are going to analyze the circuit using voltages at the nodes with a similar end result where we get a system of linear equations that we can represent in matrix form to solve for all of our unknowns all at once. And while this does require some linear algebra, especially as you get to more complex networks of resistors and voltage sources and even current sources, which we'll see in a future video, this can make it easier to solve for the circuit as opposed to slogging through a bunch of hand calculations line by line, which we saw 2 videos ago using the equivalent resistance method to solve this same circuit. So just like we needed to define what a mesh was, it would probably help if we define what exactly a node is before we do node analysis. So a node is a junction between 2 or more branches of a circuit, and a branch is any part of the circuit with 2 terminals. So we have a node at any point where 2 or more branches are connected in this circuit. So we have a node there where the battery is connected to this resistor. We have a node here where these 3 resistors are connected. We have a node down here. And we have another node over here. So we actually have 4 nodes in this circuit. And you'll have to remember we had a much earlier video about circuit diagrams. I'm going to tack on another resistor as an example here. Sometimes people get tripped up and think that anywhere 2 lines intersect is a node. So for example, if you had more resistors in the circuit, you might think you have a node there and a node there. But that node is redundant with this one over here. Remember that these wires just represent 0 resistance wires. So all of these points here are at the same voltage. That is really just one node. So we're not going to see it in the fairly simple example in this circuit, but if you have circuits where there's a lot of things connected, you do need to be careful. Oops, I erased a little too much there. That you're not getting confused and kind of adding more nodes than the circuit actually has, or you're going to make your life a little more difficult than it needs to be. So we only have 4 nodes in this circuit. And we're going to use the same problem we had in the previous 2 videos to make sure we get the same answer, where we have a known voltage source, Vs, and then we have resistor values, R1, R2, R3, and R4. And we know that those values are Vs equals 6 volts, R1 equals 1 ohm, R2 equals 8 ohms, R3 equals 7 ohms, R4 equals 0.5 ohms, and we are going to be asked to solve for the current, voltage, and power of the resistor R2. Our goal of node analysis is going to be to get a system of linear equations that we can represent in matrix form, AX equals B, where A and B are filled with constants that we know, and X is our unknowns, which in this case are going to be our node voltages, which we are going to define as variables. So before we do that, we're going to go back over to this circuit and realize that we can actually eliminate 2 of these nodes that we're not going to need to use in our analysis. So one is our ground node. By definition, we know that the voltage there is 0 volts. And since this node up here is just connected directly from the ground node to a voltage source, we know that the voltage there is going to be Vs. So if we went ahead and treated those nodes like unknowns and treated this like a circuit with 4 unknowns, we would wind up with a 4x4 matrix. You could do that, but it's just kind of going to be some unnecessary work. We can just eliminate these 2 nodes right off the bat. Again, because we know that the ground node is only 0 volts, and since all we have connected between these 2 nodes is the voltage source, we know the voltage there is Vs. So we are going to define our other 2 nodes. I'm going to call this node A, and we're going to define the voltage there as VA, that is referenced to ground. And I'm going to call this other node, node B, with a voltage VB, again, referenced to ground. So our 2 unknowns in this system are going to be VA and VB. We use linear algebra to solve for those, and then we can use those to solve for our other parameters of interest, like I2, V2, and P2. You can probably look at this and already tell that the voltage drop over resistor R2 is going to be VA minus VB. So just like with mesh analysis, how we applied Kirchhoffs voltage law around each mesh, but then rewrote the equations in terms of the mesh currents, here we are going to apply Kirchhoffs current law to each node and then rewrite the resulting equations in terms of our voltages. So we're just going to define some intermediate variables as currents here, but we're going to quickly get rid of these just to write them in terms of the voltages instead. I'm going to define lowercase I1, I2, and I3 as the currents through those three resistors. And that reminds me that I forgot something very important. Just like with mesh analysis, you need to go through and assign the sign convention to all of your resistors. And again, I discussed this more in the previous video, but if you flip these, it's not the end of the world. It just means you'll get a negative number at the end, meaning you had assumed the incorrect sign. So it's fine, whatever way is intuitive to you. Just make sure you assign these signs and then keep track of them when doing your Kirchhoffs current law, So we are going to apply KCL at node A, and we see that I have current 1 flowing into that node, currents 2 and 3 leaving, so I can write that as I1 minus I2 minus I3 equals 0, but I want to rewrite all three of these in terms of my voltages and using Ohm's law. So let's look at each resistor one at a time. First, we're going to look at R1. So again, remember, Ohm's law is always V equals IR. I have my voltage drop across resistor R1 is Vs minus Va. So that's going to be Vs minus Va. And notice how I am following the sign convention that I assigned there, where I assume the higher voltage is on the side where I have put the plus. That is going to be I1 times R1. I am going to want to substitute that equation in here for I1, so I need to rearrange that to solve for I1. So that's going to be I1 equals Vs minus Va over R1. And now I'm going to do the same thing for my other two resistors. So for resistor R2, I have Va minus Vb. Va minus Vb equals I2 R2. Again, I'm going to rewrite that as I2 equals Va minus Vb over R2. And finally for resistor R3, again I have this is in parallel to R2, so I have the same voltage drop there. Va minus Vb is going to be equal to I3 R3. Rewrite that as I3 equals Va minus V over R3. And now I can plug all three of these over into this equation to get my first equation just in terms of my voltages. So I'm going to have Vs minus Va over R1 minus Va minus Vb over R2 minus Va minus Vb over R3, all equal to 0. Now, we briefly went over the linear algebra for this in the previous videos. I'm not really going to repeat it here, but we want to get this equation in the form where we have coefficients times our two unknowns equal to our other constants that aren't multiplied by the coefficients over on the other side. So I am going to write this out all painstakingly because I'm bad at doing math in my head. We're actually going to split all of these out. So I'm going to have Vs over R1 minus Va over R1 minus Va over R2 plus Vb over R2 minus Va over R3 plus Vb over R3 all equals 0. And we're going to collect all of our coefficients for the Va and Vb terms, and we're going to move the Vs over to the right-hand side because that is a constant. So that's going to give me negative 1 over R1 minus 1 over R2 minus 1 over R3. So let's just double check. Again, you always want to keep track of your minus signs. I have a minus sign in front of each one of my Va terms there. All times Va. And then let's look at my Vb terms. I'm going to have a plus 1 over R2 plus 1 over R3 times Vb. And I'm going to move my Vs over to the other side. So that's going to be negative 1 over R1 times Vs. And I guess if all of those minus signs bother you, you could flip the sides of this equation and write this. So I'm going to add this to both sides and subtract these from both sides. You could write this as 1 over R1 plus 1 over R2 plus 1 over R3 times Va minus 1 over R2 plus 1 over R3 times VB equals 1 over R1 times Vs. Again, that is assuming that I move this over to this side of the equation, move this over to this side of the equation, and then move this over here, and then just flipped it around again to write it like this. So these equations are equivalent. Something about just having it written like this with fewer minus signs. I like this way better, but either way works. I'm probably going to use this one going forward, but you should get the same answer at the end of the day. So we're going to label this as equation 1. That is the first equation in our system of linear equations, and we are going to go over to the next slide for equation 2 since we are out of space here. So we flipped over to a clean slide here, and we are going to go through that exact same process for node B, where we have currents that we defined previously, I2, I3, and then we're going to have I4. Exiting that node, I forgot to redraw my signs and all the resistors. Again, you got to be careful to keep track of your sign conventions. Plus, minus, plus, minus, plus, minus. Okay, so we are going to apply Kirchhoffs current law at that node, where we have I2 and I3 coming into the node, so they're going to be positive, and then minus I4, since that is leaving, that's going to be negative, equals to 0. And then again, for each one of those resistors, we're going to use Ohm's Law, V equals IR, to write Ohm's Law in terms of that current and the voltage at the adjacent nodes, where remember we have 0 volts here and Vs there. Right, so let's do that again for R2. This is going to be redundant with what I did on the previous slide, but I'll do it here anyway. The voltage drop over R2 is going to be VA minus VB. That's going to be equal to I2 R2. Do that for R3. The voltage drop over R3 is also VA minus VB equals I3 R3. And the voltage drop over R4 is simply VB minus 0, since it is connected to the ground node. And that's going to be equal to I4 R4. We rearrange each one of these to solve for the current. So I2 equals VA minus VB over R2. I3 equals VA minus VB over R3. And I4 is simply VB over R4. We now take all three of these and plug them in to our Kirchhoffs current law equation. So we're going to have VA minus VB over R2 plus VA minus VB over R3 minus VB over R4 equals 0. And just like we did on the previous slide, I'm going to break this out and get it in terms of coefficients times our unknowns. So I have VA over R2 minus VB over R2 plus VA over R3 minus VB over R3 minus VB over R4 equals 0. I am going through this a little faster, but again, this is the same process we went through for node A on the previous slide. Now I'm going to collect my coefficients in terms of VA and VB. So for VA, I'm going to have 1 over R2 plus 1 over R3 times VA. And then for VB, I'm going to have plus -1 over R2 minus 1 over R3 minus 1 over R4 times VB equals 0. Again, matter of personal preference depending on how you like to write things and keep track of your minus signs. I can factor the -1 out there to make this a little neater. I'm going to get 1 over R2 plus 1 over R3 VA minus 1 over R2 plus 1 over R3 plus 1 over R4 times VB equals 0. And this is my second equation in my system of linear equations. On the next slide, we will copy both of these equations over and go through the solution using linear algebra. So here I have copied over our system of linear equations where we have our coefficients that are going to make up our A matrix. We have our unknowns that are going to make up our X matrix, and then we have our constants that are going to make up our B matrix, and again, that is all in the form of AX equals B. We went over this in the mesh analysis video, but in case you jumped straight to this one and didn't watch that one, where A is going to be a 2x2 matrix with terms A11, A12, A21, A22. X is a 2x1 matrix with X1 and X2, and B is also a 2x1 matrix with terms B1 and B2. So we can write this out in matrix form: 1 over R1 plus 1 over R2 plus 1 over R3, 1 over R2 plus 1 over R3, 1 over R2 plus 1 over R3, and 1 over R2 plus 1 over R3 plus 1 over R4 times our two unknowns. Oops. VA and VB equals our constants VS over R1 times 0. We can invert the A matrix, so we have this equation. We multiply both sides by the inverse of A, and then that gives us X equals A inverse times B, and that will allow us to solve for X. So I'm not going to do that in this video. I'm just going to go do it off screen. You can use whatever program or graphing calculator, MATLAB. I can actually just do it in Excel, because Excel will invert and multiply matrices. You plug in, notice that you know all of the values in here, you know all of the R values, and you know VS because that is given. So everything in the A and B matrices is given to you. You want to solve for X, so you can just plug and chug. And again, doing that with linear algebra and using a computer program to do it saves you the effort of manually doing all those calculations line by line, and lets you solve for your unknowns all at once. So I'm going to pause my recording for a second here, go off screen, calculate those values, and then come back and report the values for VA and VB. And before I do that, I forgot two very important minus signs. I may have gone off to do the calculation and gotten nonsensical numbers, and then came back to look for my error and realized that I forgot this. I have these two minus signs here that I forgot to carry over into my matrix. So again, be really careful that you don't lose minus signs when you are doing this, or you will get answers that do not make any sense. So, or that are maybe appear to make sense but are wrong. So I need to put parentheses around that whole term, have a minus in front of it, parentheses around this whole term, have a minus in front of it as well. The way I noticed immediately that I made a mistake, I went to have to solve this and I got a negative number for VB, which does not really make any sense in the context of this circuit. I can't, just with a battery and resistors in a passive circuit like this, with a DC source, I can't have a negative voltage here that somehow gets lower than ground. So solving this, that's a good way to do a sanity check. Got a negative number for VB, that did not make any sense. Came back to check, realized that I had forgotten my minus signs. Again, do as I say, not as I do. Don't forget your minus signs. Let's try that again. Gonna go off into Excel and crunch the numbers for VA and VB. And happily, when I do that, I now get some numbers that make sense. I get VA equals 4.853 volts and VB equals 0.573 volts. And if you remember back to our circuit diagram, we know that the voltage across resistor 2, which is one of the parameters we were asked to solve for, is just going to be VA minus VB. So I can now go ahead, remember these are my unknowns when I do node analysis, but they are not necessarily the unknowns you were asked to solve for in the problem. So I have V2 equals VA minus VB, which again, I'm being lazy and not actually checking the rounding that much here, but VA 4.853 minus 0.573 is going to give me V2 equals 4.28 volts, 28, which is, thankfully, if you watch the previous two videos, exactly the same answer that I got there, using either the equivalent resistance method or mesh analysis. So I can go on to use Ohm's Law to solve for the current in resistor 2. And if I do that, I'm going to get 0.535 amps, which again, same answer I got in the previous two videos. And then finally the power, P2 equals I2, V2, plug in the numbers for that, and you will get 2.29 watts. So all of these are the same answers that I got with three different methods after slogging through this in all three of the different videos. So the nice part about this is that there are 3 very different techniques you can use to get the same answer at the end of the day. So if you have a preference for one of these techniques, you can choose whichever way works the most for you, or whichever way you think you are least likely to make mistakes. I have actually made mistakes in a couple of these videos and worked through solving them in real time. Honestly, I think that can be helpful to see as a student, so you know that your professors aren't perfect. We make mistakes too. Sometimes we make math errors, so you can pay attention during a lecture and catch, double check the work. It is possible that we might have an error in our notes or might make a mistake if we're trying to do it real time like I did here. And that, it's okay if you make a mistake like that on your homework. It just kind of helps you see ways to double check things, go back, look for things, especially, again, with the mesh and node analysis. These minus signs will kill you if you lose track of a minus sign like I did here, and then that carries through. That will affect your final answer. Or what we saw with the equivalent resistance method earlier, where if you're just doing a lot of algebra by hand or plugging in a bunch of numbers and just doing the calculations by hand instead of all at once like this, that is very subject to error propagation. So 3 different methods. You're done with a relatively simple circuit here. We only wound up with a 2x2 matrix in our system of equations, but this can expand to much larger, 3x3, 4x4, 5x5 matrices, and can be very useful techniques for analyzing larger circuits. So you may notice that so far we have only talked about ideal batteries or ideal voltage sources when analyzing circuits. So in our next few videos, we are going to start talking about practical or real voltage sources, and we will also be talking about current sources, which we haven't dealt with at all so far.